So we have a new kind of function, vector-valued functions. As with any kind of function, we need to be aware of what the domain of our functions are. For vector-valued functions, we have to be a little careful because one vector-valued function will have many real-valued functions packed inside of it. And so there's going to be some sort of interaction between the domains of these individual functions, right? So for the vector-valued function to be defined, all coordinate functions must be defined. So all coordinate functions should be defined. Well, where are these functions defined? So let's, I have x's here. These should be t's. Sorry. So let's look at our x-coordinate function. Let's find the domain of our x-coordinate function. So because of the square root, we can't take the square root of a negative. So the stuff inside the square root, t plus 4, that needs to be greater than or equal to 0. And then we can solve this inequality to figure out what it is telling us about t. So move the 4 to the other side, and we get t is greater than or equal to 4. So I'm gonna plot this on a real number line. So, I'm sorry, t greater than or equal to minus 4. There we go. All right. So looking just at our x-coordinate function, the domain of the x-coordinate function is t values greater than or equal to minus 4, like this. Okay, what about our y-coordinate function? Well, for our y-coordinate function, we're taking the natural log of something, so the thing inside the natural log had better be greater than or equal to, strictly greater than 0. So 6 minus 2t had better be strictly greater than 0. And then again, we can solve this inequality. Move the 2t to the other side, 6 greater than 2t, and then divide both sides by 2. 3 has to be greater than t. So for our y-coordinate function, our t values have to be less than or equal to 3. And then for our z-coordinate function, well, 7t squared, this is defined for all reals, right? We never end up with any problems trying to evaluate 7t squared. So for our z-coordinate function, it's all real numbers. So to find the domain of the vector-valued function r of t, we need all coordinate functions to be defined. So over here, to the left of minus 4, the x-coordinate function isn't defined. So even though y and z are, x isn't. So we can't allow these t values, right? Because x wouldn't exist, and that doesn't make sense. Over to the right of t equals 3, so this is the t-axis here. Over to the right of t equals 3, our y-coordinate function isn't defined, and so we can't have these t values either. So the upshot of all of this is that the only t values that make sense for this vector-valued function are t values from minus 4 up to 3. Including minus 4, but not 3. So I guess we would have to say that the domain of this vector-valued function is, let's see, from minus 4 up to 3, so t has to be greater than or equal to minus 4 and less than 3. All right? So the upshot of all of this is that the domain of a vector-valued function is the overlap of the domains of the individual coordinate functions. Okay? So overlap is sort of geometrically what's happening, but the sort of fancy math word for that is intersection. So the domain of a vector-valued function is the intersection of the domains of the coordinate functions.